All right, last unit of the year, oxidation numbers. So we've heard of the term things oxidizing and stuff like that. For example, if you have iron like on a bike and it's sitting out there and there's no protectant on it, either grease or paint or something like that, it's going to be exposed to the elements which contain oxygen, and that's going to rust. Just for fun, let's go ahead and make this into Fe2O3. So we say that the iron is oxidized. Now, that was an old way of talking about this and calling things that react with oxygen oxidized. And then that means that what the oxygen is basically being reduced. You cannot have oxidation without what's called reduction. So one way people look at this is they do something like oil rig. If you've ever heard of an oil rig, this will give you a decent idea of how to remember this. Oxidation is a loss of electrons, and reduction is a gain of electrons. So that's the basics of it. So we know that iron here would have just as many electrons as it does protons because it's neutral. So we say that it has an oxidation number of 0 currently because it's in its elemental form. So oxidation numbers themselves are a way of maintaining or bookkeeping how positive or how negative something is, its character. Remember, electrons have a charge of negative, so that means if you lose electrons, you become positive. Well, here we have always called this in this formula, this is iron oxide. But if we recall, it has a particular Roman numeral here which determines its charge or tells us its charge. In this case, this is iron 3 oxide because the iron here has a positive 3 charge. So if we have on this side, the oxidation number goes up, the element has been oxidized. Iron in this case has been oxidized. And here, this is elemental oxygen, so it has an oxidation number of 0. And here we know oxygen always has a charge of -2. We're actually going to find out that that's not always the truth, but that's what we've used up to this point. We're going to start seeing other ways that oxygen can be used. So here it has a charge of -2. So it went from 0 to 2, so oxygen is reduced. So here's the oxidation of iron and the reduction of oxygen. Now, how did I know these were zeros? Well, it's all based on the number of electrons they've lost or gained. And here are some rules for assigning oxidation numbers. When we add this up, just like we've always done before, the summation of these, the number of electrons lost and the number of electrons gained, has to be equal to 0. So plus 3 times 2 plus -2 times 3 equals 0, because here we have 6 and here we have -6. We also would want to go ahead and balance this. So we need a 2 there, a 3 there, and a 4 here. Because it does take 4 of these irons to make 2 of these iron oxides. Another way that you could look at this is that even if the elements themselves weren't balanced, we'd have to do it to make sure that the electrons lost and gained are balanced. And that will become important as we go through this. So as I said, rule number 1 for assigning oxidation numbers is that when you add up the elements or the atoms in a molecule or ion, it has to be equal to the charge. Since this has no charge, when we add them up, that has to equal 0. So here, if we add this up, it has to equal 0. So if we use the rules that we've been used to in the past, hydrogen forms a +1, oxygen has a -2. When we add this up, it has to equal 0, so that will allow us to find sulfur here. And normally we would say sulfur would do a -2, but in this case it isn't a polyatomic ion, so it's not going to be following those changes that we're used to. So if we take a look, 2 times the oxygen, since there's 2, so that is 2. Plus, there's only one sulfur, so I'm going to dub that as X for right now, or 1X. Plus, we have 4 oxygens, so that's 4 times -2, which is -8. And that all has to add up to 0. That means that the X must be, or sulfur must be, +6. And watch this real quick. If this were the polyatomic ion S-2, we could do the same thing, except for they have to equal -2. So oxygen, there are 4 of them, so that is -8. X minus 8 has to equal -2. So again, the sulfur is 6. Now, I know this is quick. You're going to have to stop and rewind this and go over this several times. The other thing is, if you don't know these rules, you can't really do this. So the oxidation number for pure element is 0 because they've neither gained or lost electrons if they're in their elemental form. The number of electrons must equal the number of protons. We know some elements, group 1A, 2A, and silver, zinc, and aluminum, as well as fluorine. These have these set charges all the time. That's why we've never really had to put Roman numerals with them. If you're in group 1A, your oxidation number is +1. If you're in group 2A, it is +2. And fluorine always has a -1. Now, hydrogen usually has a +1, unless it's not. And this is where people get so confused is, they're like, well, how do we know when it's not? That's the thing. It's usually +1. It's not +1 if it can't be +1. This is calcium. Calcium has to have a +2. If hydrogen is +1, then this total would be 4, but we don't see a charge out here, so it has to be 0. So that means if the calcium is +2, that means each of these hydrogens must be -1. And that's the cool thing. Hydrogen is going to either be +1, -1, or if it's in its elemental form, 0. So you only have those 3 choices. Oxygen is usually -2. What if it's not? Well, here's the thing. These rules, the 1 always has to be true. 2 has to be true. 3 has to be true. And here we have some rules that aren't necessarily true. It says usually by it. Well, we go with the rule preceding. These rules are of more clout. They're more overbearing the other rules. So let's take, for example, H2O. Sure, hydrogen is +1, and oxygen is -2. We add that up, that equals 0. Let's take peroxide, right? I'll have H2O too. So if we take a look here, the rule preceding says, well, 1, they have to equal 0. 2, hydrogen is usually +1. That rule comes before, so that takes it